Hey everyone, in today's video we're going to have a look at ELECTRA, a model created by the Google AI team. And in the last couple of videos we've looked at the Go Emotions dataset, which is also released by the same team. And in that dataset we had to perform some text classification on Reddit comments. In the previous video we've also seen how we can use the pre-trained tokenizer. And now I'm going to show you how you can basically create ELECTRA model from the pre-trained checkpoints, and this is provided by the HuggingFace Transformers library. Let's get started. So the ELECTRA model, and along with the pre-trained checkpoints, was released by Google AI in 2020, and there is a blog post on aigoogleblock.com, and here it says more efficient NLP model pre-training with ELECTRA. So basically the authors were trying to find a more efficient or faster way to train transformer models. And in the case of ELECTRA, they've actually replaced the mask language modeling task with token replacement detection. I'm going to show you how they do this in a bit. And they create a very interesting analysis or comparison between the ELECTRA model and other models. So we can really see that the ELECTRA model is very much more efficient compared to the some of the BERT or Roberta or other variants of the well-known large transformer models. So the first thing that we are looking at is the masked language modeling task. And as you can see, we have some example. The chef cooked the meal. And in the mask language modeling task, the idea is to mask some of the tokens with the mask token. And the model has to predict what is the token that has been masked. Okay, so that's pretty much standard, and most of the models that you have so far or you've heard of based on BERT and similar architectures are based on this task. But the authors created a bit of a newer task. So the idea here is to detect whether or not a token has been replaced. So instead of masking the text, they are just replacing the tokens, and part of the model, in this case ELECTRA, the task of the model is to classify whether or not this particular token was replaced or is it the original one. So these are the building blocks of the ELECTRA model. And when we actually merge those two ideas, we are, or the authors of the ELECTRA model have come to this architecture, which is basically two transformers. And the first one is a generator, and the other one is a discriminator, which is going to be the actual ELECTRA model in which we are interested in. So this is pretty much something similar of a training setup to GANs, but this is just for text. So what we have here, again, we have the example, the chef cooked the meal, and we are masking some of the tokens. Some of the details of how many or how much of the tokens were masked can be found in the paper, which we are going to have a quick overview in a minute. But the task here was to replace some of the tokens at random. And then the task of this first model, which is called the generator, is to predict the actual tokens that were masked. So in here, we are replacing the masked tokens with A and 8, which are, of course, not the original ones. And the idea behind this discriminator is to detect whether or not every particular token is replaced or is it the original. So this is the training setup. And here we have a very interesting graph, which shows that basically ELECTRA is much faster at training, and with fewer resources you can train basically those ELECTRA models, and those achieve very high glue score, at least on the datasets that the authors were using. And this is pretty interesting because you can effectively get this ELECTRA model, and instead of using the pre-trained version, maybe you can do a pre-training on your own dataset and then fine-tune on this one. So this is something a bit different compared to BERT or other models, because when you're pre-training BERT, you will need a larger resources, and this is not really the case with ELECTRA, so you can maybe pre-train with that. So these are some of the results. Of course, the authors from Google Research published the source code for the ELECTRA. There is a GitHub repo, and we have 3 variants of the model. We have the small, the base, and the large. So in these videos, we are going to use the base model, or we are going to fine-tune it. And you can have a look at the different performances of those models in the paper, actually. So this is the paper. It's available on the archive. It's called ELECTRA Pre-training Text Encoders as Discriminators Rather than Generators. So it's a mouthful, but still. So we have the same graphic right here. And the authors are basically showing again another graph, which shows us the comparison between the size of the generator and the discriminator. And purely empirically, they found that the larger the generator size, it doesn't mean that the performance is going to be better. And when training those type of models, the interesting part is the clash between the discriminator and the generator and the discriminator, because basically you're trying to tune both of them. But if the generator becomes too good for the discriminator, then you might end up with very jacked lines for learning, or your models might not converge at all. So there are some hacks that are mentioned in this paper, which you might want to have a look at if you are interested in how do you train some kind of similar models from scratch. But yeah, it's a very interesting idea, and it's very different compared to the all of the other transformers that we have. So yeah, let's continue with the ELECTRA documentation that is available on the HuggingFace Transformers library. And here they are basically summarizing what I've just said. And the good thing from here is that you have the Google checkpoints, and there are a lot of different ELECTRA models here. So you can see we have the basic ELECTRA model, the one for pre-training. We have a special class for mask language modeling, sequence classification, multiple choice, token classification, etc. Of course, you have the options to use TensorFlow or maybe use JAX, but I'm not going to go into those. The good thing about this documentation is that you have complete examples of how you can use those models. And yeah, we are going to actually include some of those examples in the notebook that I'm going to show you in a bit. Next, I want to show you the actual small generator, which is available on HuggingFace. Here we have a pipeline, which we are going to have a look at. And this pipeline is used for few masks. So we can basically do something like this. I'm going to compute this. And you can get the idea that this pipeline for filling the mask with the ELECTRA small generator is doing some work and then predicting that the goal of life is life. Okay. And we have the same thing for the discriminator. Again, recall that the discriminator is the actual model that we are going to fine tune, but we are going to have a look at the generator as well. All right, so let's get to the notebook, and in there we are going to have a look at the different types of ELECTRA models and how we can play around with those. So I'm going to update the dependencies here. to the latest versions. I'm going to install this. I'm going to terminate my other session, and hopefully Google Co-op will let me to connect to this. All right, so it seems to be working. And I'm going to basically run all of the code that we had so far. Okay, so while this is running, I'm going to continue with the next couple of steps that we have right here. So recall that we had this pipeline for filling the mask, and this is basically using the ELECTRA generator. And I'm going to set up pretty much the same thing by running the import from the Transformers library and then feeding some custom text. So to create the pipeline, I'll need the name of the task. And yeah, I'm currently using Vim bindings for Google Co-op. So the task name is fill mask. And you can basically take a look at the different tasks that are offered by the Transformers. Pipeline. Yeah, so if I go to this, there is this fill mask pipeline, which is a class from the Transformers library. And here they have all of the parameters. And yeah, you can have a look at the pipelines that are supported by the Transformers library. Honestly, I'm just using those pipelines to have a look at the basic model capabilities. I'm not using those to create anything that is going to be fine-tuned or whatever. I'm just going to use it to show you what those models are capable of. So if we go to the model, this will be Google ELECTRA base generator. And I'm going to pass in a tokenizer as well. And I'm going to copy and paste this. All right, so I haven't done this. All right. Okay. So the tokenizer is done. And then we can request how many results do we want. So this should give us the top 3 results. Okay, I'm going to run this. And then I'm going to write a sample text, which we are going to run through this pipeline. So I'm going to again take this. All right. So the text that we have, so everything has run thus far. I'm not superstitious, but I'm a little, and then we are masking this. So this is the example text that we have. And I'm going to just run this through the pipeline. Also, I need to import the JSON module. Okay, so this is downloading the model now. And I want to execute the fill mask on the text. And I want the result to be nicely indented. So here are the top 3 predictions for the masked token. So the first one is naive, then it's different, and then it's arrogant. So none of those are actually correct, but this is pretty much expected given the interesting part of the text. So you can see that you are given a score, which tells you what is the confidence of the model for this particular token. Then there is a token ID, and then you're given the complete sequence with the replaced mask right here. So let's have a look at another example, and hopefully this should be a bit easier for our model. So would I rather be feared or loved? Easy both. I want people to be afraid of how much they mask me. All right, so another quote from a very famous guy. And here I'm going to basically take this, copy it, and paste it right here. So this time the model is very confident that the token is love, which is the correct one. So we have very good prediction. And then the next best guess is hate, so love and hate. And then we have the need, which is again something that this particular character feels for different people. So okay, so we had a look at the generator, and the generator is basically replacing those tokens, those mask tokens. But let's have a look at the discriminator next. Let me just write down this here. So how are we going to use the discriminator? Recall that the discriminator job was to get the tokens and decide whether each token has been replaced or is it the original one. And in our case, I'm going to use the ELECTRA for pre-training model. For pre-training. And I'm going to load the checkpoint for pre-training from pre-trained. And this will be the discriminator. All right, so how all of this works. Let's have a look at some text again. I'm not superstitious, but I'm a little yoga. So this is the text that we're going to give to our discriminator. And it has to recognize that yoga has been replaced. So let's run this through the tokenizer. And get the outputs of the model from the encoding. So let's have a look at the outputs. So the outputs contain this widgets property. And you can see that we have some scores. And the number of those scores are actually the number of the tokens that we have into the encoding. All right, so we have 16 here and 16 here. But recall that some of those are actually special tokens, which is the first one. And I'm going to show you just the tokens now. So this will be a bit easier to understand. Okay, so we have all of the tokens, and as you can see, the classification token and the separation token are here. So these are the first and the last one. So those basically should be ignored, but their scores are quite low. So we have this, and then actually the discriminator job is to, at least from what I understood, is to detect whether or not one particular token has been replaced. So we have a single replaced token here, and I'm going to basically take it, the widgets, and I'm going to run them through a softmax function. So this will basically give us a probability distribution with a sum of 1, which is great. So this will basically tell us what is the probability that each token has been replaced. And I'm going to write a single function that shows us for each token whether or not it has been replaced. So first I'm going to take the replaced token index from the widgets, which is pretty much the same thing, but I'm going to take the argmax, or the index of the replaced token. Then I'm going to take the special tokens from the tokenizer. Because we want to skip all of the special tokens. And then I'm going to iterate over all of the tokens. And if the token is in the special tokens, then we are going to skip it. Otherwise, if we are at the replaced token index, I'm going to print the token, and I'm going to just say that it has been replaced. Otherwise, this will be an original token. So this should work, I guess. So to run through this, I'm going to call the function show detections, which we just wrote, get the tokens, and pass the widgets. So recall that we had the tokens. I'm not superstitious, but I'm a little yoga. So as you can see, we have all of the original ones, and the yoga has been marked as replaced, which is correct. So this time the discriminator is working quite all right. And in the next example, the quick brown egg jumps over the lazy dog. So I guess you know which token is the replaced one here. And I'm going to take those. And I'm going to take this as well. And if we run this, you can see that we again have a correct prediction that the egg has been replaced, or is the replaced token. So this is very good, at least from the pre-trained model. All right, so now that we know about the generator and the discriminator, we are actually going to throw out the generator and just take the discriminator and fine tune it. So to do that, I'm going to create a bit of an interesting extension to the HuggingFace library. So here we are going to write the emotion classifier. And I'm going to create a class called ELECTRA classifier. And this will inherit from ELECTRA pre-trained model. Pre-trained model, yeah. And here I'm going to pass in the config. So the ELECTRA pre-trained model, I need to actually include this. So let me go to the imports at the top. Okay, so now that we have everything imported, I'm going to continue with this. So here I'm going to take the number of classes, and just bear with me on this one. I'm going to show you why we're creating our own classifier. So this is the ELECTRA model. I'm going to pass in the config, and the classifier is going to be ELECTRA classification head. And then I'm calling init weights or post init weights, and I'm going to override the forward method. Okay, so how all of this should work? We are going to pass in the input IDs to the ELECTRA model and the attention mask, and this should return the discriminator hidden states. And once we have those, I'm going to take an output of the classifier or the classifier head by taking the discriminator hidden states, the first value of it, and taking the widgets from the classifier, which is again the extra classification head. And this is pretty much taken from the original source code of the HuggingFace Transformers library. So this should be pretty much taken from, let me see actually. I took it from the modeling ELECTRA file, and I'm going to have a look at the ELECTRA classification head. Yeah. I basically took this from the ELECTRA for sequence classification. And the idea here is that I want our model to just return the widgets and not the was. So let me just rewrite this to post init. And because this is basically the newer version of the library, and they made that change. So when this is done, I'm going to continue with the emotion classifier. And this should extend from the Lightning module. So we are actually building our model in here. And I'm going to initialize this with the number of classes that we have. All right, so again, I'm going to get those. And I want to get the model classifier. So this will be our ELECTRA classifier, which we just created. And I'm going to take it from the pre-trained model. And I'm going to pass the number of classes that we have here. And I want to create a loss calculator. And here I'm going to use the cross entropy loss from Torch. I probably need to create another import for this to work. From torch import nm. All right. Cross entropy was. And then we have to override the forward method. And I'm going to just pass the input IDs and the attention mask through the classifier. So what is required to run PyTorch Lightning, LightningModule? So this is basically our model here. So we overrode the forward method. Then I need to basically overwrite the training step method. So this method will be called with a batch and a batch index, a batch of data. When we are training the model, then we are going to do the same thing when we are validating. And again, the same thing when we are testing. And I'm going to fill in those in a minute. The next required method is the configure optimizers, from which we are going to return Adam W, which is the Adam optimizer with weight decay fix. I'm going to pass in the parameters of the model, which is in this case are not the parameters of the classifier, but the parameters of this module. And then I'm going to pass in the warning rate, which is going to be 1 times e on minus 4th. And this warning rate is basically given to us from the authors of the ELECTRA paper. Nothing magical right here. So let me do the training step in here. So basically all of those steps are going to be the same, but we are going to be at different stage. So I'm going to create a method run step. And here I want to take the input IDs, the attention mask, the labels, and convert those to wonk. And I want to get the widgets of the model or the output. So I'm going to run the input IDs and the attention mask. This will basically call the forward method right here with the parameters that we're giving it. And then I'm going to calculate the loss for this step. I'm going to use the cross entropy loss. And here we are going to use this stage parameter to walk at the particular stage. I want to call this on the each step, on each epoch, and when we are showing the progress bar. And I'm going to return the loss here. So this is pretty much the training loop, which is replaced by the LightningModule right here. So I'm going to call this method run step, and I'm going to pass in the batch and that we are on stage train. Then I'm going to do the exact same thing, but for the validation step, and then for the test step. And this is pretty much the minimum model, at least on my book, that you must have in order to use PyTorch Lightning for fine-tuning. So this is pretty much it for this video. We've seen how we can actually use the ELECTRA model, the generator and the discriminator, the difference between those, and we had a quick look at how the whole model was trained. And I've shown you how you can use PyTorch Lightning with the Lightning module to incorporate the pre-trained model. And in the next video, I'm going to show you or walk you through the whole training process and a couple of hacks or tricks which I like to use when training such models. And thanks for watching, guys. I'll see you in the next one. And please like, share, and subscribe. The whole notebook with the code will be published when I finish up this series. And leave your questions in the comments down below. Bye bye.